Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so very happy to have Mike Hamburg, who was an undergrad here at Harvard, and then went on for a PhD at Stanford, where he did some nice work like circular secure encryption and efficient non-pairing identity-based encryption. And I also hear that he's a good chess player. And
I don't know who you heard that from.
That's not accurate. Poker, at least?
No, not really.
Not really.
Bridge, maybe. I don't know. Anyway.
But a decent programmer as well. Is that also inaccurate?
It's accurate, and if it weren't, I wouldn't admit it.
Okay. Okay, so let's hear about broadcast IBE.
Yeah, so this is joint work with Dan Bonnet. Okay. So this is a variant of identity-based encryption. In identity-based encryption, it's sort of like public key encryption, but the basic idea is that your public key is your name or any other string, but some say uniquely identifying string. So as a concrete example of this, as always in crypto, Alice wants to send a message to Bob. So she encrypts it just using his name. So you notice here that Bob doesn't have intrinsically any secret, like he didn't generate his name. So in order for him to read the message, he's going to have to get a secret from somewhere. So there's this other entity, the PKG, that holds, which stands for private key generator, who holds sort of a master secret key. And after Bob has appropriately proved that he's Bob to the PKG or done something else out of band, the PKG will send him a secret key that corresponds to his name. And then he can use this secret key. He just has to do this once. He can use the secret key any number of times to read messages that are sent to him. So this design was proposed by Adi Shamir in 1984, but it wasn't until 2001 that it was built independently by Cliff Cox out of GCHQ and by Dan Bonnet and Matt Franklin. So most implementations of this that you'll find are based on the Bonnet-Franklin design, and they use sort of elliptic curves and bilinear pairings as their functionality. And this talk also uses elliptic curves and pairings. So in any case, following on mostly to the Bonnet-Franklin work, there's been sort of a cottage industry of at least what Dan calls adjective-based encryption. And so some of these are changes to the security model. So like anonymous IBE is a change to the security model where you don't want people to be able to see what the message is to. Some of them add delegation, like hierarchical IBE. There are some that add sort of fancy models for deciding under what conditions somebody can read a message that you send. A lot of this is the work of Brent Waters. He's the W in most of these. Yeah, so there are all sorts of different things, but the important takeaway from this slide is there's a million of these, and they all have a separate construction. And what's worse, they all have a separate security model. So despite the fact that if you read one of these papers, you can sort of predict what the model for the system and its security is going to be, they're all sort of defined separately and proved separately. So the goal here is to define a unified security model that describes all of these systems, or at least most of them, and then including support of the variant security models and delegation and so on. And additionally, to design a toolbox that enables you to build these systems without being a cryptographer. Not necessarily all of the systems above, but sort of many systems that have similar attributes. And this is a very flexible toolbox, so you can build, you can have more adjectives than the other adjective-based encryption schemes. Really?
Faith-based, he asked.
This doesn't solve faith-based encryption. So the model for this.
Right.
The whole field is faith-based.
This is sort of true, actually, but I'll get there at some point. So the model is based sort of on lattice-based access control. I would call it lattice-based encryption, but that's something else. And so I'm trying, yes, a different kind of lattice. And so I'm trying role-based encryption for the name, but that might change. So the idea here is that you have some sort of hierarchy of identities or roles, as they're called, and there's a sort of blue arrow between them. Colors show up kind of. Anyway, there's a blue arrow between them, which means that the CISO, for example, using her secret key, she can create a secret key for the VP of Finance and the VP of Engineering, and they can create keys for Carol in Finance and Dave in Engineering, respectively. So this hierarchy doesn't have to be a tree. It just this one happens to be a tree, but and it doesn't have to have a single root. Although the model sort of
Does that mean that somebody gets two different keys, or that you need two different inputs to be able to have a key?
It's actually it's an either or. So it might be that there's somebody under both the finance and engineering or something, and then either one of those VPs could create that key. It's an or, yeah. So the arrow means sort of can delegate to, or has power over, or something like that.
Is security downwards broken? So if somebody manages to crack sort of the
Yes.
of the VP of Finance, everybody under him is compromised?
Yes. The positive light to cast this in, at least depending on your corporate IT policy, is that there's implicit escrow built into this model. Also, so if you want to avoid the problem...
What does it mean to say that A can create B's key? I can create an RSA key out of nowhere. That's presumably not what you have in mind.
Right. So when you encrypt in this model, let's actually just forward the slide, half a slide. So when you encrypt in this model, you choose a policy from some set of policies. And the policies also participate in this partially ordered set. But the important thing to note is that the policies are just they're strings, or they're objects in some abstract set of policies that doesn't have any information that's derived from secrets in it. Instead, there's sort of one master public key, and at least conceptually, there's one master private key. Whether anybody has it or whether we destroyed it when we set the system up is a different question. But so in this model, sort of the CISO has the master secret, and then in order for anybody to decrypt any message, they have to have some sort of a secret, because it's something that's not generated by them, because the process of encrypting a message doesn't take any input from the person, the role or whatever you're encrypting it to. It just uses the master public key. So, right. So the answer is that Dave can't generate his own key because nobody listens to his input, such as the role of an engineer. So he needs someone to generate it for him, and this hierarchy is the description of who can generate keys for whom.
Well-defined
his public
as-
key is already well defined as sort of like the combination of the master public key and his name. Before he has any input into the system. Anyway, so the policies participate in this partial order also, and so there's also there's a transitivity of these arrows. So like the CISO clearly can create a key for Carol. She just creates a key for the VP of Finance and then uses that key to create a key for Carol directly. It's not like she has to actually give the key to the VP of Finance. And it may be that there's a way to do this directly, but similarly, the CISO can read everyone's email. And the VP of Finance can read Carol's email. And if you want to avoid this, it's possible. You just sort of like make another role underneath the VP of Finance. That's sort of like the VP of Finance's personal key, and the other one is like the VP of Finance's sort of like escrow key, and it's locked in a safe somewhere or something like that. But anyway, so this is the basic model, and then so what does it mean for a design like this to be secure? Oh, sorry. There are a couple of other things that are in this model. So one of them is collusion resistance. This is sort of the positive way of saying it, but it means that two people teaming up from this diagram can't do anything other than what they could do by themselves. So for example, Dave and the VP of Finance, despite the fact that they've got a finance person and an engineer, they can't read, or I mean, despite the fact that they've got a VP and an engineer, they can't read the VP of Engineering's email, for example, by teaming up. Some systems actually do have some form of collusion, like you need certifications from two different entities in order to do something. But in this case, that's verboten. And then there's also path independence. So the model stipulates that any design that you're doing within this model has the property that Dave's key looks the same no matter who generated it. So it could have been generated by the VP of Engineering, or it could have been generated by the CISO directly. And it should look the same in either case. It should be from like the same distribution of keys.
It seems like not having this would allow auditing of where the key came from. And are there situations where you don't want to know where it came from?
The real issue is just that it complicates the model. And similarly, decryption is sort of path independent. So the decrypting one of these messages should have the same results no matter who's doing the decrypting, even if the message is malformed. And the advantage of this is that when you talk about the model, you don't have to, you have a smaller attack surface, because instead of attacking, like trying to attack Dave's key as generated by this path of delegation versus his key as generated by this other path of delegation, you don't have to worry about that. And similarly, you don't have to worry about decrypting a message with this key instead of this other key. It's just mostly a formal thing.
Also, like for anonymous, if you want one of the variants was anonymous, for that you will need this kind of property, or it's not enough anyway?
I don't think you necessarily need this property for anonymous encryption. But it does make the model a lot simpler in any case. So, like with all crypto systems, this wouldn't be complete without a security game, which is what it means for this system to be secure. So this is a game between an adversary, represented by FreeBSD, and a challenger, which sort of represents the functionality in the system that the adversary might have access to. And the game sort of amounts to the adversary's goal is to try to do something that he couldn't have, that he shouldn't be allowed to do within the functionality of the system, within the sort of explicitly provided functionality of the system. So the challenger sets up the system and sends the sort of master public key to the adversary. And then the adversary gets to make as many queries as he wants, and they can be of 3 different types. So he can choose any role in the system, and the challenger will give him a secret key for that role. He can also choose any ciphertext and say what policy the ciphertext was encrypted under, and the challenger will tell him, will decrypt the message for him. Of course, if the ciphertext was malformed, the challenger might send him back, an error string or something like that. But Yeah, so he can decrypt any message that he wants, even if he doesn't have the key for it. And then at one point during the game, any point in this sequence of queries, he can choose a pair of policies and a pair of corresponding messages. And the challenger will flip a coin and encrypt one of those messages using one of those policies, and send the resulting ciphertext back. Let's assume the messages are the same length, so we don't have to get into that can of worms. And so the idea is that within the functionality of the system, the adversary shouldn't be able to tell which message was encrypted and under which policy. This is an anonymous version. And at the end of the game, after he's possibly made more queries, the adversary guesses what B is. And then he wins if he's correct, except that he doesn't win if he asked for a secret key that's supposed to decrypt one of the policies he requested, because in that case he's supposed to be able to read the message. And he doesn't win if he asks the challenger to decrypt the challenge ciphertext, because, of course, in that case he's also supposed to know what's in it. And so the security property should be that the adversary doesn't win this game much more than half the time, half plus epsilon. So there are variants to this, because there are several variants of these models. So one of the common ones is that a lot of the schemes that are designed in this area are selective, because it's very hard to prove things in this full game. And selective means that the adversary has to know who he's attacking before the game starts. This is a sort of realistic assumption.
Policy 1, policy 2 in the...
He has to choose policy 1 and policy 2 in advance.
Before the public parameters.
Before he sees the public parameters, yeah. But the public parameters still have to be from the right distribution. But the usual reason for this is that the challenger sort of encodes some hard math problem in the public parameters in such a way that to open one of the messages is equivalent to solving the math problem or something like that. A number of these designs can't handle anonymity, so that means that you can sort of tell something about which policy a message was encrypted with. So in order to say that the adversary doesn't learn anything from this, he should still be able to not tell apart two messages encrypted with the same policy. So we just say that the two policies are the same.
Why policies rather than just public keys or the name?
Well, because this is they're more general than just a name. So the goal is to sort of build on identity-based encryption to make a system where you can choose, when you encrypt a message, a policy that describes under what circumstances the message can be read. And so...
Maybe broader than just saying some subset of people should be able to read this?
I'll get there. Maybe I should have said this earlier, but it's later in the talk.
And just as a curiosity, I mean, all of these, if you can prove security under your previous slide, then it's secure under any of these.
Yeah, but these are weaker notions of security. And another one would be that, like, maybe you can take a ciphertext and like tweak it into another ciphertext for the same message, for example. So in that case, the adversary would, if he gets to make decryption queries for anything other than the exact ciphertext you gave him, then he'll be able to sort of read the message. But maybe you say, look, okay, you can't make decryption queries after you've been given the challenge, or maybe not even at all. And so those are also weaker notions of security. So any questions about the model before I move on to the construction?
So there was one of the various adjectives was hierarchical things. And how is it different from yours? Which is partial. I mean, it sounds like...
So this model describes sort of all of these different variants. So the difference in hierarchical is that in hierarchical, the structure is a tree. It's fixed to be a tree of a specific shape, and no other setup.
All those variants are equivalent to your notion, except they're like, this is a set of policies we support. For example, IBE supports only policies which is just immediately descendants of the root.
Yes.
You can only encrypt to this, like, and so on. You know, files
And yeah, and which roles? Yeah, which roles and which policies they support.
Right. So, because you said all of them have separate definitions. I mean, aside from anonymity, I think it's exactly what you said, right?
Right. So this is an attempt to unify the definitions that are used by
policies, right? Over the allowable subset of policies. So that's the only variable, right? I'm saying
the allowable roles and policies, and I guess how weak the security model is. But other than that, those are the only sort of variables.
I'm not sure if I should bug you about this. Now, are you going to describe the policy language, how expressive it is? Because you said questions.
So here, right. So in this part, the policy language is completely abstract, and sort of the question that's I'm about to deal with is, what sort of a policy language can you build? So, for example, you can build attribute-based encryption, and then there's whatever policy language Brent can dream up, and then So the toolbox that I'm going to describe to build these things is something called spatial encryption. And the idea is that the roles in this, the things to which you can assign keys, are all the affine subspaces of an n-dimensional vector space. And you say that given the key for some space, like say a big plane, you can create a key for any space that is inside it, like any line or point in that plane. And then the policies are points, and the key for a role, which is some space, can decrypt a message encrypted to some policy if the point lies inside that space. So this is a sort of abstract notion, but the idea is that if for every role in your hierarchy of roles you assign a subspace, and for every policy you assign a point in such a way that the roles nest appropriately and the policies are inside the right roles, then this will provide an implementation of the design that you want.
So the dimension of the different policies is different, is it? Can be different.
Well, the policies are points.
The rules.
Yeah, the dimensions of the roles can be different.
These are affine subspaces?
Affine subspaces.
So this obviously captures a tree, but how does it capture something that's not a tree?
Okay, so as you pointed out, this obviously captures a tree. So for example, if you have a tree of depth n, and you have some sort of paths in that tree, then you just have you assign to that the affine subspace that has the first k coordinates fixed, and the rest can be anything. So this is obviously an affine subspace, and similarly the policies are the same things with the rest of the coordinates set to 0 or to some fixed value. Also, you should notice here that usually home is a string and not a number, so you need some way to encode it as a number, because mod p or whatever. And a collision-resistant hash function is enough. I guess here technically you need to be a collision-resistant hash function that never outputs 0, but whatever. But you can build other things besides HIBE with it. So for example, you can build Broadcast IBE, where every message goes to any subset of the users of size at most, I guess, n-1 here, where n's the dimension of the space. And the way you do it is that you give Alice, you treat the vectors in this space as polynomials, just as the coefficients of polynomials or whatever. And you give to Alice all the multiples of the polynomial x minus Alice. So this is a vector subspace, in fact. And then when you want to encrypt to Alice, Bob, Carol, then you just encrypt to the point x minus Alice, x minus Bob, x minus Carol, and because polynomials uniquely factorize, then only Alice, Bob, and Carol can read this message. And they, in fact, can read it because it's a multiple of their because it lies in the space of multiples of their name. So Alice is a string which we hash to a number, and then the role that she gets is corresponds to the vector subspace, which is all the polynomials that are multiples of x minus Alice.
It's a one-dimensional vector space.
It's an n minus one dimensional vector space.
Codimensional.
Yeah.
It's a codimension. Yeah.
All multiples of x minus
Policies
Alice.
in all of these.
All multiples of x minus
All,
Alice.
all polynomial multiples, not scalar multiples. Yeah.
How much are you giving up here? The thing is, compared to general lattices, they're going to be modular. These are all going to be modular, right? So is this, I don't know whether the sort of geometrical framework is something ad hoc made to make the security proofs work, or whether, for example, modular lattices are really sort of genuinely more tractable than general lattices.
Well, so I don't actually know what a modular lattice is, but
Basically, it's the type of lattice that, more or less the type of lattice that has a geometrical representation like this, although you may need slightly more general representations to capture the full class. Anyway, we can talk more about this
we
later,
can talk more
since-
about it later. So I think an answer to your question is that as long as the lattices are kind of small, then you can build them easily using sort of any variety of known techniques. But when the lattices are big, so here there's things parameterized on small sets of strings, for example, then constructing them in general is open and, in fact, probably impossible because the description of the lattice itself is going to be exponentially large. But it may be that there are other classes of lattice that would be interesting to build and could be built that can't be captured in this framework. I don't know how you would design those. I mean, attribute-based encryption makes some things that don't look like vector spaces as far as I know, but yeah, this does provide a sort of a wide variety of possible lattices to build on.
For broadcast also IBE, so when you say maximum number of users is n minus 1.
That's the maximum number of users to which you can send a single message.
Because usually I saw in broadcast IBE, it's kind of, well, in general broadcast encryption maybe it's kind of the opposite. The universe is potentially could be exponential and you would want to essentially encrypt to everybody but like 5 people.
So you can do that too, but that's there are different notions of it. So this sort of broadcast IBE is useful if you're sending an email, for example, and you don't want to have a separate ciphertext for each user, but rather one short ciphertext that sort of captures all the people that the email is addressed to. As opposed to if you're broadcasting a television show and have some number of revoked keys from people whose players have been compromised or something like that.
Just to make sure I understand, so in my mind, policies are names, and so here a policy is a polynomial. So say Alice wants to read email that was broadcast to her. How does it translate to actually get to
The actual mechanism is a little bit abstract. The point is that the policy Alice or Bob or Carol maps to a point in a vector space, and Alice has a key that reads any point in some subspace of the vector space, which happens to contain the point Alice or Bob or Carol.
So you can't explain to me how it works exactly.
So how it works is that how is it best to describe it? Well, let me take this offline if I've got time afterwards.
So the number of maximum users is actually p minus 1, right?
The number of maximum users is more or less unbounded, but the maximum number of users that you can send a single message to is n minus 1. Because the degree of the polynomial is going to be...
I thought that p, I don't know, I'm confused between, I guess...
Right, it's p if you have a...
Polynomials mod p, but...
Yeah, it's p if you want your hash function to be bijective, but if it's just collision resistant, then the number of the users are just strings, so...
But the maximum number of users, that can be like exponentially large. It's just that it will take you a linear work in in the number of actual users you need to construct a message for.
Yes. And when you set up, n is fixed when you set up the system. So.
The exponential.
No, it can't.
Because n is the dimension. Okay.
N is the dimension. Yeah.
Okay.
Right. Anyway, the other thing about this is that you can use this to build Broadcast HIBE with a sort of quick modification on this scheme, and this is the first sort of construction of Broadcast HIBE. But you have a question?
No, I just wanted everybody to pipe down a little bit.
Oh, okay, yeah.
Sorry.
So there are a lot of other things that you can do with this. So for example, suppose that you're not comfortable with the idea of a single authority that can read everyone's email. As you can see, I gave this talk at IBM before I gave it here. Suppose that you have some authority, let's say that they're VeriSign, they move into this business. And they give a key to IBM.com, and then IBM gives keys to the users who have email addresses there. So this is a sort of hierarchical IBE kind of a design. And in fact, like I said on the last slide, we're doing Broadcast HIBE. So Alice has this message, and she wants to send it to Bob, Carol, and Dave, and they work at IBM and Microsoft. And she also says in the message which CAs that she trusts. And say that's VeriSign and CA-cert or whatever. So then Bob and Carol can read this because they have a key to the right email addresses, something on the to list, and something that was generated by VeriSign. But if, once again, FreeBSD is the enemy here, if someone gets a key that says bob at IBM.com from some evil CA that's not trusted, the evil CA is not on the trust list, then they won't be able to use that key to read the message because it doesn't have the right properties. So the general version of this is something called product schemes, and the goal is sort of to add extra adjectives. So here we're adding multi-authority as the extra adjective to the scheme. And the idea is actually quite simple. So the to field of this message is a broadcast HIBE. You choose multiple users in this sort of hierarchy. And so you can implement it in ZP to the n for some, n that you choose. And then similarly, the trust setting is actually a broadcast IBE because you're choosing a set of different authorities just by their names. And then, so that you do that in ZP to the m for some m where m is like the maximum number of authorities plus 1 or something like that you want to be able to specify at a time. And then, so when you have a role in this system, it is represented as a vector subspace, or an affine subspace of ZP to the n, and an affine subspace of ZP to the m. So their direct product is an affine subspace of ZP to the n plus m. And similarly, when you encrypt, you get a point on each side, and the sort of pair of those is appointed in ZP to the n plus m. And it turns out that this hierarchy actually does what you want it to do, which is it sort of enforces this this and relation here. So each key has one sort of attribute from each of the designs that you're producting, and then you can delegate only if you can sort of delegate on both sides. So for example, IBM.com can delegate to Bob at IBM.com in the HIBE design, and then VeriSign can delegate to itself on the Broadcast IBE side, and so this this link is allowed. On the other hand, this link is not allowed because while Bob at IBM.com reads the policy, the HIBE part of the policy, this evil CA doesn't read the trust part of the policy, so this is not allowed. And it turns out that you can do this much more generally. So you, in most cases, don't actually have to choose this N and M ahead of time. You have to choose sort of the maximum dimensions allowed ahead of time, but you don't necessarily have to choose, it turns out, how you're partitioning the space and how you're encoding everything ahead of time. I'm sort of continuing to explore that in my work on policy languages for this, but yeah. So so anyway, yeah. Question.
You just told us there is no single super key, or there is.
Right. So there sort of is. There's a single super key that's created when the system is set up, and then you divide it among all the authorities, and then you destroy it. Yes, or another thing that you could do is you can use secret sharing, and this is compatible with secret sharing. So you can make it so that 10 of the most trusted authorities, if 8 of them get together, they can create a new authority, for example. And similarly, if 8 of them get together, they can read anyone's email. But
Otherwise, if I wanted to destroy that super key, I would have to create all the authorities first.
Yes.
Okay.
Which makes more sense if you're talking about deploying this within a company where you give each department their secret key and then destroy the root or something like that. Yeah.
In all fairness, this is like single authority scheme. Usually when people say multi-authorities, they mean independent key generation. You can't do independent key generation.
Can't do independent key generation. Right. So that's actually sort of what I was saying about collusion resistance. So because a lot of times the multi-authority schemes are in fact by design not collusion resistant, and so I can't even model them. So a quick note about how this is built. It's based on the Benet-Boyan Go HIBE. And so the public parameters and the secret keys are O of n, where n is the dimension. But the ciphertexts are constant size. So in the initial construction, the ciphertexts are actually just 2 group elements. So they're 40 or 64 bytes or something like that. And in the there's a sort of enhanced version with a bigger security proof or a better security proof where the ciphertexts are a little bit longer, but only by a constant factor. So the sort of enhanced security proof is based on Waters' recent work, in particular the Luca Waters HIBE. It provides adaptive security, which is the strong notion. It provides anonymous security according to the definition, but not necessarily in practice because, well, you can't determine who a message is to based on just looking at it. You also can't decrypt it without knowing who it's to. So it's sort of not really anonymous in some sense. Yeah.
Are you saying the definition of anonymity is insufficient, or you're saying there's some other property of anonymity that you'd like to add?
In some sense, the definition. I should probably put a note in the thing on the definition of anonymity. So the definition of anonymity in that's usually given is that you can't tell who a message is to by looking at it, sort of. But the real question is, then can you decrypt it if it's to you? And usually in anonymous IBE, this is sort of a non-issue because you only have like some small number of keys and there's no hierarchy, so you just try all the keys. But in the case where there's a hierarchy, this definition is a little bit insufficient because you can't just try all the possible policies that are below your role in the hierarchy because there might be exponentially many of them.
So your subspace has exponentially many points.
Exactly. Okay. Even if it was one-dimensional, it would have p many points where p is huge. So unless it's zero-dimensional, which is possible, the definition of anonymity is a little bit weak. So maybe I should change the security model to point this out.
So in existing hierarchical, for example, like weaker notions of this role-based thing, is it actually true that if I'm at some point and there is a ciphertext which is suspected to some of my descendants, but I have no idea where, because it's also exponential, I can just test? I mean, do existing IB schemes have the same, let's say HIB schemes? Do they also have
I
the
think
same
there's an
deficiency?
anonymous HIBE scheme out there. I think.
Which don't have this deficiency, right? This is like a correctness issue.
Yeah, it also has this deficiency. Yeah. Right. So the security assumption for this is static, but like the Lugo Waters assumption, it's kind of nasty. So I'd like to improve it to something that's less nasty, but as it is, it's some fixed size but ugly thing. There's a variant in prime order groups. I actually like the variant in prime order groups better because despite the assumption being nastier, you don't also have to assume that factoring is hard, for example. And you don't have to have your group big enough that it's unfactorable, unlike in the Lugo Waters or whatever, where it has to be huge. The original variant is prime order and more efficient by a constant factor, but doesn't have a proof of adaptive or anonymous security. So there's a bunch of work left to do on this. I hope to have at least some of it done by the time my thesis is due, which is in June or something like that. So I want to clean up the assumption, change it into some nasty thing with 1 million terms, into some more simple thing. I have an idea about how to fix the anonymity issue, but almost sort of necessarily at the cost of ciphertext size, because the thing about having complicated policies and constant size ciphertexts is that the ciphertext itself is certainly not enough to determine what the policy was, even if you do have the key, because it's not big enough. And so at least with the foreseeable way to fix this, you'll end up sacrificing ciphertext size if you want to make use of that. There's a variant called co-spatial encryption, where the policies are sort of, instead of being a point, the policy is like also a vector space, and you can decrypt if it intersects. This enables you to build circuits and emulate sort of more of attribute-based encryption. You build like threshold gates and OR gates and stuff in a way that it's harder to build with the regular design here, the regular spatial encryption. Unfortunately, the proof of security, at least in the interesting cases where some components can be parallel to other components, is the new adaptive fancy dual system security proof doesn't work for it. So if you don't want to be stuck with selective security, then I need to improve that. And then, like I said, I haven't fully designed a policy language. I have some ideas for how to make one, but nothing final yet. So I'd like to sort of design a policy language and then actually sit down and implement this so that you can see how fast it runs and how easy it is to use. And so that's all. So any questions about this part of the talk?
Better get to the other part.
The other part's just one slide. I've done some other work, especially in the area of implementing crypto systems. So one thing is a fast and flexible software AES. This is the fastest implementation of AES that doesn't use hardware instructions and that can do sort of any mode. There's a faster one if you want to do just counter mode. It works on Power Mac and on certain Intel chips. It also works on the more recent ones, but they have hardware AES, so why bother? It avoids this attack where normally you implement AES using big lookup tables, but there's an attack based on sort of the fact that looking things up in a lookup table alters the state of the CPU's cache, which means that an attacker can sort of see what you're looking up. I also did a JavaScript implementation of AES. It turns out that I think no actual cryptographer had done this before. because I ended up with a very small and fast one compared to what else is out there. And then a recent thing that I did was sort of silly project to add crypto to video games to make it harder to cheat in certain ways. And to do this, because video games have a lot of data that they shuttle back and forth, to do interesting crypto, you have to make it really fast. And there's some sacrifice of security, but if a game is going to last an hour, then it's fine if you make a key that can only survive against a supercomputer for 6 months, and then the big feature here is that, unlike say OpenSSL, which takes almost a millisecond to do an elliptic curve group operation, this takes about 12 microseconds. So
you still just do it for the handshake or something, right? Or
no, it's for it's actually oblivious set intersection. So the idea is that to prevent you from seeing your opponent's units in a real-time strategy game that aren't actually in your field of vision, you do an oblivious set intersection of your field of vision, which is, of course, just as secret as where your units are, and the locations of your opponent's units. And then, based on the results of that, you know where his guys are that you can see and not the ones that you can't see. It's a two-party computation, yeah.
But can you cheat in move your field of vision in ways that are not compatible with the motion in the game?
So you can cheat in other ways, but the idea is that at the end of the game, all is revealed, the secrets are given away, and then your opponent can check by emulating your view of the game. I mean, his game will automatically check by emulating your view of the game that you didn't cheat. But there's no way to sort of automatically check at the end of the game that you didn't siphon the memory of the application and look at where his units are in memory, which is something that happens actually surprisingly often in real-time strategy games.
So honest but curious security here is good enough
because you can check at the end.
Sounds important.
So that's all.
Ask a question about the first part of the talk.
Yeah.
So I'm trying to understand. So there is the partially ordered set, which was trying to tell us who can delegate their keys to whom, or who can sort of simulate who else. There is the aspect of the policies where you're saying there is a broad class of things that can be done, but you don't have an explicit language which describes exactly what can be done.
So the model part is trying to model other people's work in the field and also this work in general. So there are many different policy languages that people have built. So the model doesn't specify a policy language. It just says the roles and policies are some partially ordered set. Together they make a partially ordered set.
So the partially ordered set somehow also captures the policy itself.
Yes. It captures both the roles and the policies. And then what partially ordered set depends on what design it is.
And the n that you're choosing is a function of this partially ordered set, or is it?
Well, so then the second part of it, I guess I didn't organize this talk well enough. The second part of it, the question is sort of how can we build interesting partially ordered sets in general? So you can't build all of them. And in fact, that ought to be impossible to build every one of them because there are too many of them. But you can build, the following interesting class of things that can be embedded in a vector space of dimension n for some n that you choose.
You mentioned this issue that so you have this value bound of n possible users.
Yeah.
And the actual public key is linear in n.
Yeah.
And also you can't really have a collision resistant hash function into n the domain n because it's
into the domain p. So there are p total users or something, or there are any number of total users, but then there are only n that you can send a message to at once in a single ciphertext.
Okay.
It's just for the multi-case.
It's for
a specific example, right?
yeah, or there's a or n is maybe the size of the depth of the tree, but then like at every step it's like a p array tree where p is huge. So there are exponentially many positions in the hierarchy, and it's exponential in a huge number, but the exponent is only n, and that's the depth is only n.
That example of the broadcast, it kind of saves you a factor of n essentially. You're saying
exactly.
The secret key, well, kind of, in the sense that the secret key, instead of in the standard scheme, if I just have my secret key,
yeah.
Right, and everybody has a secret key, but if I want to encrypt to 25 people, somebody just, somebody has a ciphertext of size 25, so you kind of trades it off.
And it could be quadratic, for example. So if you also wanted to have, n different authorities, then it would be like, you'd need like n squared ciphertexts, and then that...
At least for basic things, it's kind of the opposite, the usual. The ciphertext usually is 25, my secret key is 1, and here you say
here it's the reverse.
25, the ciphertext is 1.
Which is a little bit easier to deal with because, if your secret key takes a couple kilobytes on disk, then fine. But you'd rather not append a couple kilobytes to every email.